you probably have a pretty good idea about what resistance is. The resistance to the flow of charge. But we have to be a bit more careful about it, and to do that we're going to look at the mathematical definition of resistance, and we're going to then have a look at what affects the resistance of a resistor. I want to start by making this really clear. Resistance equals potential difference divided by current. R equals V over I. That's it. That's how you calculate resistance. But that's not enough for a lesson video, so let's dig a little deeper. What is resistance in an electrical circuit? And perhaps more usefully, what does a resistor do? So here's our basic circuit with a cell, an ammeter, a resistor, and a voltmeter across the resistor. If the cell has an EMF of 6 volts, the resistor will have a PD of 6 volts, which is shown on the voltmeter. That's fixed. That's controlled by the cell. It has an EMF of 6 volts and it is driving the circuit. The resistor is also fixed. It is an object in the circuit and it has a fixed value for its resistance because that's how it was made in the factory. Let's say it has a resistance of 3 ohms. The function of a resistor in a circuit is to limit the current. The resistor reduces the current. We know the EMF, so we know the PD across the resistor, 6 volts, and we know the resistance, 3 ohms, and we know that R equals V over I, which rearranges to I equals V over R. So I is 6 over 3, 2 amps. The resistor has controlled the current, making it 2 amps. This is simple but important. The current does not control the resistance. The potential difference does not control the resistance. The manufacturer, the factory, controls the resistance, and we bought it, we stuck it in the circuit, and now the resistor limits the current. Simple but fundamentally important to understand. Okay, now we know that the resistance is controlled by how the resistor is made. What actually controls the resistance? There are 3 basic things we can control when we make a resistor. What it is made of, the material, its length, and its cross-sectional area. In other words, we're controlling the material and the volume. Let's try an analogy first. Imagine a room full of people, a dance studio in fact. We've got some K-pop going on. There's a door on this side and a door on the opposite side. There's music playing, people are happy, lively, dancing around. And now you come in this door and you want to get to the door on the other side. You move in, but you've got to dodge here, duck here, swerve here, and you get to the other side. You felt some resistance to getting through because all these people were dancing. But you did get through. Imagine if the room was longer, with more people dancing away. You'd find it harder to get through. If the room was wider though, your ducking and swerving would make it easier to find a route through. You could find the gaps and dodge your way past everyone. If we change the people to T-Rexes, we'd find it really hard to get through since a T-Rex has some pretty killer moves and it swings its long tail around. But then if we cool the room down, cool it right down, the cold-blooded dinosaurs would go to sleep and it would be easy to get through again. In a wire, these things are like changing the length of the wire, changing the cross-sectional area of the wire, changing the material of the wire, and changing the temperature of the wire. 4 things that can affect resistance. So, the material is important because if we have a metal like copper, it has free electrons, and the free electrons can move around carrying the charge. Something like plastic does not have free electrons, so there is nothing to carry current around. It's an insulator. Even if we stick with metals, copper is great at conducting, iron is good, but not great. Different metals have different abilities to conduct electricity, which is quite obvious and reasonable, I think. And we record that in a property called resistivity. I can go to a textbook and look up the resistivity of copper. It's 1.7 times 10 to the minus 8 ohm meters at 20 degrees C, so it depends on temperature as well as the material. Iron is 9.7 times 10 to the minus 8 ohm meters at the same temperature, so it's over 5 times as high. You probably don't actually need to know about resistivity at GCSE level though, so let's move on to something more useful. Length. This one is quite intuitive really. If we think of resistance as resistance to the flow of charge, if a charge has to go through a longer piece, it experiences resistance getting here, but then still has to continue and get over here, so there's more resistance. In fact, doubling the length doubles the resistance. So resistance is proportional to length. By the way, this is how we define proportional. It doesn't just mean as length increases, resistance increases, so please don't state that. It specifically means as length doubles, resistance doubles. Next, we have cross-sectional area, which is not quite so intuitive. Again, if we think of resistance as being the resistance to charge flowing through the material, if we have a thin wire, the charge can get through but has to avoid all these atoms. If we have a thick wire, the charge still has to get through, and there's more atoms, but now it has more possible routes to get across. If going this way seems a bit blocked, it can go this way. So that's one way to explain why, as the area gets bigger, resistance gets smaller. A bigger area means more options for the flow of charge. Mathematically, resistance is proportional to 1 over cross-sectional area. R is proportional to 1 over A. And those are the things that control the resistance of a resistor. R is equal to the resistivity times length over cross-sectional area. You probably don't need to worry about resistivity, but you do need to know that if you halve the length, you're going to halve the resistance. And if you halve the cross-sectional area, you're going to double the resistance. Be careful though, because we are talking about cross-sectional area. So if you halve the diameter, that means you're going to quadruple the resistance because the area of a circle is equal to pi r squared.